In this video I will go over a pricing example to illustrate the model that we looked at in lecture notes. So I'm going to assume that you've looked through the lecture notes and of course that you attended lecture, and here are the notes from my website, and we're going to use these notes throughout this video. Now, what we had is we set up a pricing model. We have our profit, but now, so we'll write profit here as we usually do, revenue minus variable expense minus fixed expense. And originally we had it as a function of Q when we were doing CVP analysis. Price, variable expense per unit, and fixed expenses were were constant, and the only thing the company controlled was how many units to produce. That assumed that the company was a price taker, that there was perfect competition, so to speak, so that they didn't really get to choose their price. They were just given a price and they had to go with it. But what fits the world a little better is the case where we have imperfect competition, where firms are no longer price takers, but they're actually price setters. So they get to influence the price. They get to actually choose their price. So profit, more realistically, is a function of price, and the quantity demanded, which I don't need to write the word there, but the quantity demanded is also a function of price. It's a linear function of price. In the lecture notes we wrote it like this. This representation of quantity demanded reflects the law of demand, that whenever price rises, demand falls. So what we did is we took Q and we substituted it in for Q up here and up here, and that means our profit function can be rewritten as negative b times p squared plus a plus bvp and minus av plus f. And you saw this equation in the lecture notes. I'll go to it real quickly. Right here, equation 3. And so what I want to do now is, you'll see that the only unknown, p is the variable. The only unknowns, the only unknown is p, and the constants are b, a, v, and f. So I want to set up an example where I give you a, b, v, and f, and then we'll ask several questions related to this model to test your understanding of the model. So suppose A is 10,000 units. That is, whenever the company gives the product away for free, so price is 0, the demand is A, right? Q would be A then in that case. And that can be at most 10,000 units. B is 800 units, so that means for a $1 increase in the price, the demand will fall by 800 units. And then the variable expense per unit is $5. Let's just assume that. So it costs the company $5 to make each unit. And let's assume that the fixed expenses are $10,000 a unit. So here's our example. Let's rewrite the profit function then, substituting in up here for B and A and V and F. And you'll find that we have our profit then as a function of price is negative 800p squared plus 14,000p minus 60,000. Whoops, maybe I shouldn't. These are our givens. So let's go over some questions here. So number one, the most obvious question and probably the most important question is, what price will the firm charge? And you can answer that question. They're going to charge the price that maximizes profit. So the better question is, what price maximizes profit? Let's let's graph what we have before we answer this question. So if we graph profit against price, here's our function here. It's a quadratic polynomial of degree 2. We know that the leading coefficient on that polynomial will tell which way the quadratic opens, either up or down. And since the coefficient on the p squared is negative, we know that the quadratic opens down, or the parabola, if you want to call it that, opens down. So we can actually completely draw this thing. Let's see. We know it intercepts the profit axis. When price is 0, what's profit? It's negative 60,000. So down here, I kind of want to draw it to scale. Maybe we'll... What? We're going to use this drawing throughout this video, so I kind of want it to be to scale. So we have something like this. Something like this, right? I'm not very good at drawing, but you can imagine an upside down parabola. And we know the price that maximizes profit, there's only one of those, right? It's a unique price, and it occurs at the peak of this function here. We'll call it P max. And the profit that they would earn at P max would be over here at this value. We'll solve for that later. So the question is, what is P max? Well, it turns out we can use calculus to figure out P max. Notice that the slope of the tangent line to this function at P max, here's the tangent line. The slope of the line of this tangent line is 0. Notice that. It turns out that the derivative of a function is the slope of the tangent line. Those are two synonymous concepts. So what we need to do is take the derivative of the profit function. We'll abbreviate it as pi prime. Another notation for it is d pi dp. This tells how the profit changes for an infinitesimal change in the independent variable, or in the price. The derivative of the profit function, if we can calculate this, that will give us the slope of the tangent line at any point p. Then we just set that derivative equal to 0 and solve for p. That will give us P max. So we're taking the derivative of our profit function right here, and all we have to do is take the derivative of each piece and add those derivatives up, and that will give us the derivative of the whole function. This is because the sum of the derivative of a sum is equal to the sum of derivatives. So the derivative of negative 800p squared, we take the coefficient, negative 800, times the exponent, or the exponent times the coefficient, if you want to think of it like that, times p to the power of whatever it was before minus 1. So this would be negative 1600 p to the power of 1, or negative 1600 p. Then the next one, 14,000 times p. You take the power, which is the exponent, which is implicitly a 1 here, we just don't write it. 1 times 14,000 times p to the power of 1 minus 1, or p to the power of 0. Well, anything to the power of 0 is just 1, so we just have 14,000. And then negative 60,000 right here. We can rewrite this as negative 60,000 times p to the 0, right? Because anything to the 0 is 1. And we just do the same form. We take the derivative the same way. We take the exponent times the coefficient times p to the power of 0 minus 1, or p to the negative 1. But it doesn't matter because we have a 0 out here, and 0 times anything is 0. In other words, the derivative of a constant is 0. So here's the derivative of our function, of our profit function. And this gives us the slope of the tangent line to the function at any point p. So for example, if we pick this point right here, call it P star. And we found out where we were on the function right here. And we take the tangent line to the function right there. And we want to know the slope of that line. What do? We just put in that point, P star, into the derivative function. And so intuitively we see that the place where profit is the most is where the tangent line is horizontal, right, at the top, and where the slope is 0. Well, this function right here, this derivative function, tells you the slope of the tangent line at any point P. And if we want the slope to be equal to 0, we just set it equal to 0 and solve for P. And the P we get from solving this equation right here will be this P, right? It'll be the P at which the slope of the tangent line is 0. In other words, the P at which profit is maximized. Or in other words, the P at which the derivative is 0. Those are all the same thing. Just 3 different ways to say the same thing. So let me get rid of the clutter here. Alright. So we're setting this thing equal to 0 and we're solving for P. And I've already done this in the lecture notes for a general profit equation, but I haven't done it where I actually had numbers. So we isolate P, we're going to have negative 1600 P equals negative 14,000. So P equals 14,000 over 1600, or negative 14,000 over negative 1600, but the negatives cancel. And we're going to call that P max. It's not just any P, it's a special P. And it equals, if you do the math, it's $8.75 per unit. So if they charge $8.75 for each of their units, then they will make the most profit. We could see this from the lecture notes. We can do the formula in the lecture notes if you want to do that instead of taking derivatives. I mean, it's the same thing as taking derivatives. I've already done it in the lecture notes, but I've given you the formula that results A plus BV over 2B. You'll see we get the exact same thing. A plus BV over 2B equals 10,000 plus B, which is 800, times 5, which is V, over 2 times 800. That's just 14,000 over 1,600, right? The same thing as I wrote. So that answers the first question. Question 2, what quantity will be produced at P max? Produced and sold, right? We're assuming lean production here. If they produce it, then they sell it. Not necessarily right away, but eventually. They don't ever have units left that they produced that they never sold. So what quantity will be produced at P max? Well, we just use our quantity demanded function, right? Quantity demanded as a function of price. What was it? It was A minus BP, or 10,000 minus 800 times P. And that means that quantity demanded at that particular price, P max, is equal to 10,000 minus 800 times P max, or 10,000 minus 800 times P max, which is 8.75, 3,000 units. So those are the profit maximizing price, $8.75, and quantity demanded at that price, 3,000 units. The third question, we have to do a little more calculation to answer. What are the break-even price quantity combinations? Notice I said combinations plural, right? Because there are 2 of them. Call them P1 star. There are 2 prices, P2 star. 2 prices at which the company will earn 0 profit, and therefore at those 2 respective prices there will be 2 respective quantity demanded amounts as well. And what are these? Well, we have our profit function is a quadratic And you probably recall from and we're wanting to set the profit equal to 0 and solve for p, right? This should look familiar to you from high school, maybe even before that. So somewhere in your grade school, you solved quadratics like this, and what did you use? You used the quadratic formula, right? So we find that there are two p's, and we can go straight and use the lecture note formulas if we want to. Right here for p1 star and p2 star, we can use these right away. But let's just do this right here without using those. You'll get the same answer. It's equivalent to using those, but there are two prices. So there's in general, p will be so it's negative 14,000 plus or minus the square root of 14,000 squared minus 4 times the coefficient on p squared times the constant, right? All divided by 2 over the coefficient on p squared. And this is plus or minus. So in general, that's what the those are the roots of the equation. They're the two values of p that make the polynomial equal to 0. In other words, the two break-even prices in this context. So we want p1 star is going to be the plus 1, and p2 star is going to be the minus 1. So we just put the minus sign right here. And if you solve for p1 star and p2 star, you will get, let me go ahead and move this down a little bit. You solve these equations in your calculator, or you put this all into your calculator, you're going to get the p1 star is $7.50 per unit, and p2 star is $10 per unit. So these are the two break-even prices. If they charge $7.50 per unit or $10 per unit, they're going to earn 0 profit. Now the quantity demanded at these prices will be different. The quantity demanded at P1 star is just found by taking P1 star and putting it into our quantity demanded function, right? And when you do that, you would get 10,000 minus 800 times P1 star. Whoops. P1 star is 7.5 here. And so you get 4,000, I believe. 4,000 units. And whenever you do it for P2 star, you will end up getting 2,000 units. So they charge $7.50. They will sell 4,000 units and earn 0 profit. If they charge $10 per unit, they will sell 2,000 units and earn 0 profit. So let's label, on the diagram, let's label P1 star is 7.5 and P2 star is 10. Notice that they're equidistant from the profit maximizing price. And you might not be able to see that as far as my drawing, because my drawing is not to scale. But the distance here, the horizontal distance is the same, right? Namely $1.25 difference. So that points out a shortcut. If you solve for P max and you use that equation, that long equation, the quadratic formula to get P1 star, 7.5, then you can find P2 star. Just take the distance between P max and P1 star and add that distance to P max, right? Turns out there's a shortcut to getting the profit maximizing price. You don't have to take the derivative, and therefore there's a shortcut to getting the there's not a shortcut to getting the roots. I don't believe, but there is a shortcut to getting the profit maximizing price if you have a quadratic function like this. The shortcut is, which I didn't talk about in lecture notes, but P max, what we did is we set the derivative equal to 0 and solve, right? That will get you P max in general for any function. But if it is a quadratic, what we can do is we can say that P max is equal to, see if I can remember this. I'm not sure if I remember. I think that's the formula, but I'm not for sure if that's right. Yeah, it is right, actually. Yeah, all right, so here, let me, excuse me, let me do this differently. If we have a profit function like this, it's a function of price, and in general, if we just label it AP squared plus BP plus C, and we set it, forget about setting it equal to 0, there's our function, there's our quadratic. Then the value of P that maximizes this function is negative B over 2A. Or the value of P that optimizes this function is negative B over 2A. If A is a negative number, then this will be a maximum, because the the quadratic will open downward, and this will be a maximum. This P will give us the value of P right here. It'll give you this, we'll call it P max. It'll give you the independent variable value. To figure out the actual maximum, you have to put that P max into the profit function. But anyway, if A is a negative number, then this will be a maximum, and if A is a positive number, then this will be a minimum. We just take the coefficient on P and divide it by, take the negative of that divided by 2A. That's a shortcut to getting P max. So when we can prove that shortcut. Our profit function was this. And I could prove this. I mean, you can use this derivative to show it's true as well, but if we prove it, we just, as P max equals 14,000 over 2 times 800. And I took a negative sign, so which is exactly 8.75. Same thing, right? It's 14,000 over 1,600. So you get the same thing as what we did when we did the derivative. Anyway, that was an aside I might not should have done, but just so you know the shortcut. Anyway, so let's go on. So those are have we answered the three? Yeah, we answered the 3 questions. Now we need to go into some more detail with this model and ask a few more questions. We're going to ask 4 more questions related to the model. Before we do that, though, let me go to my notes here and have a look for a second. All right, I want to talk about a price effect and a quantity demanded effect regarding a price increase. So I'm going to give you a few more notes that you probably want to put in your you can count these as lecture notes, even though they're not on my website. But so when price increases, that leads to revenue either increasing or decreasing, depending on which effect, and the effects are the price effect, or we'll call it the quantity demanded effect, depending on which effect dominates. So when price goes up, revenue will either go up or down depending on depending on which effect dominates, either the price effect or the quantity demanded effect. What's the price effect? Price effect is a price increase leads to revenue being affected positively. Positive effect on revenue. And the quantity demanded effect is this idea where a price increase leads to the quantity demanded going down, right? That always happens according to the law of demand. For normal goods, when the price of the good goes up, the quantity demanded of that good goes down. The quantity demanded effect would be this notion that when the price goes up, quantity demanded falls, and I guess quantity demanded falls more than the price goes up, which leads to revenue being affected negatively. So the question is, when we're asking ourselves what happens to revenue when price goes up, well, it depends on which effect dominates. Now, it turns out there's a shortcut which we can always look at to tell us which effect will dominate. And that shortcut is the price elasticity of demand. Whoops, why did I just write that word twice? I know I wrote it twice. I'm already thinking about what I want to say next and completely forgetting about what I'm writing. So the price elasticity of demand, we labeled it like this in lecture, will tell us which effect dominates. So what do we have here? So I'm going to write something down. You're going to also want to add this to your notes. If absolute value of the price elasticity of demand is greater than 1, then an increase in price leads to a decrease in revenue. So for when the quantity demanded for a good is relatively elastic, this means relatively elastic demand. This implies relatively elastic demand. Whenever quantity demand is relatively sensitive to a price change, when you increase the price of a good like that, the quantity demanded, of course, is going to fall, and that effect, quantity demanded effect, is going to dominate the price effect, and revenue is going to fall. However, if the price elasticity of demand for a good is less than 1, so the quantity demanded for a good is relatively inelastic, then whenever you increase the price of that good, the price effect will dominate the quantity demanded effect, and revenue will go up. So this is important. And then finally, we're in this case where price is increasing, so let's stay in that case. If price goes up, and revenue increases, then profit has to increase. This should be obvious. When price goes up, revenue will go up if the price effect dominates. If we're in this case, if the price effect dominates, revenue will go up. But when price goes up, quantity demanded always goes down, right? No matter what. Quantity demanded always goes down whenever price goes up. So if the price goes up and the price effect dominated and revenue went up, then profit has to go up. Why? Because variable expenses went down, but revenue went up. If revenue goes up and the revenue goes up and the expenses go down, then profit has to go up. Why do we know that variable expense went down? Well, because the quantity demanded went down. Right? If the price goes up, quantity demanded has to go down. Therefore, V times Q has to go down. V is a constant, doesn't change. So, again, if the price goes up, and we're in the case where the price effect dominated, such that the revenue went up, then we know profit went up, because the revenue went up and variable expenses went down. That's that. price goes up and revenue goes down, so the quantity demanded effect dominated, then it depends on variable expenses. It depends on what happens to variable expenses when analyzing what happens to profit. So profit will go up if variable expenses falls faster than revenue. We know variable expenses will fall, right? Because the price went up, which means the quantity demanded went down. So V times Q has to go down. And in the other case, where price goes up, quantity demanded effect dominates, so the revenue goes down, then profit will go down if it turns out that the variable expenses fall slower than P times Q. If revenue is falling faster than variable expenses, then the profit has to go down, right? So you should memorize these things right here. Gosh, I hate not being able to do one of these things quickly. Alright, so we can answer, I think we can answer the questions now that I want to ask. So let's go over some more questions here. So question 1, what is the price elasticity of demand at the profit maximizing price? Well, this will just give you some practice in calculating price elasticities. So the price elasticity of demand at the profit maximizing at P max, we can label it like this. And let's actually calculate the absolute value of it. So that would be equal to, from the lecture notes, we know the price elasticity of demand is just percent change in quantity over percent change in price. Percent change in quantity is just, let's go and look at that for a sec. If we go to the lecture notes, here we go, right here. Percent change in quantity is just the change in quantity over the original quantity. And percent change in price is just the change in price over the original price, right? So if we rewrite that, that's just change in quantity over change in price times price over quantity. We can see really quickly that the price elasticity of demand will be changing depending on where we are on the demand curve, right? Change in quantity over change in price actually is fixed, doesn't change. But P over Q, this ratio P over Q, depends on where we are in the demand curve. If we graph the demand curve, we have P, we have Q of P. We know it's downward sloping, right? Whenever price goes up, quantity demanded falls. Depending on where we are in this demand curve, the price elasticity of demand for the good will be different. For example, if we're right here, then this price, call it P1 and Q1. Then P1 over Q1, this ratio right here, is going to be different than if we were right here, say at P2, Q2. P1 over Q1 is different than P2 over Q2. But change in quantity over change in price is going to be constant. It's just the slope of the quantity demanded curve. And that's constant. The slope's the same, but the ratio right here, P over Q, is going to be changing. So let's go and use our derivatives, though, to find change in quantity over change in price. This part of the price elasticity. This is nothing more than the derivative of the quantity demanded function with respect to price. So we're taking the derivative. What is the quantity demanded function? It's 10,000 minus 800p in our particular example. We're taking the derivative of this. Take the derivative of each piece like we did before. The derivative of a constant. What's the derivative of 10,000? 0. What's the derivative of negative 800p? Remember, it's p to the power of 1. We take 1 times the negative 800. That's just negative 800. And then p to the power of 1 minus 1. P to the power of 0. Anything to the power of 0 is 1. So we just have negative 800. So the change in quantity over change in price is negative 800. That's just the slope of this line, right? That tells us that the price elasticity of demand in general, let's just say in general, at any price, in our particular case, is going to be equal to negative 800 times P over Q. Now we can calculate the price elasticity of demand at various actual prices, now that we have the formula for it. So the price elasticity of demand, or the absolute value, I'm sorry, I should be saying the absolute value of the price elasticity of demand, but I don't want to say that's too long to say, so I'll just say price elasticity of demand is at the P max would be negative 800 times times P max over the quantity at that P max, call it Q of P max, equals negative 800 times 8.75 over 3,000, right? Because our profit maximizing price was $8.75, and we produced 3,000 units at that price. We got those answers earlier in question 1 and 2 of the video. So you can see here that the absolute, if we take the absolute value here, I should be taking absolute value, you get 2.33, which is greater than 1. So quantity demanded for this good is relatively elastic at the profit maximizing price. So the answer is 2.33. Just to show you that the price elasticity of demand changes as we move along the demand curve, let's calculate the price elasticity of demand at, say, one of those break-even points that we found. Let's calculate it at P1 star, for example. So here we would get negative 800 times P1 star over Q of P1 star equals negative 800 times P1 star. What was the first break-even point? I believe it was $7.50. And how many units did we produce at that? What was the quantity demanded at that break-even point? I think it was 4,000 units, if I can recall correctly. So when you calculate this, you're going to get 1.5, which is bigger than 1, but it's less elastic. Still relatively elastic because it's bigger than 1. So elastic demand, but not as elastic as when we're charging 8.75. In other words, if we're charging $7.50, we're making zero profit, and we want to increase the price, say an epsilon unit, so an infinitesimal increase in the price. Quantity demand is not going to fall by as much as if we're at 8.75 and we want to increase the price. Because why? Because quantity demand is not as sensitive to a price change at a price 7.5 as it is at 8.75, because the price elasticity of demand is lower, right here, smaller than the 2.33. Question 2. At what price will an increase in price lead to revenue going down versus going up? Well, to answer this question, we can look at what I gave you right up here. Use this right here. When the price elasticity of demand, or the absolute value of it, is equal to 1, right, then we solve for that price. That will answer the question that we're asked. Because as soon as we increase the price past that price, then the price elasticity of demand will all of a sudden be bigger than 1, and revenue will start to go down versus go up. If we lower the price past that price elasticity of demand, or the absolute value will be less than 1, and revenue will go up. Right? So I'm sorry, if we're at a price below that price, if we're at a price below the price at which the price elasticity of demand is equal to 1. So there's only one price that makes the absolute value of the price elasticity of demand equal to 1. There's only one price that does that. If we're at a price below that price, then an increase in price from that price that's below that particular price, and we increase it a little bit, revenue is going to go up. But if we're at a price above the price that makes this thing equal to 1, if we're at a price above that and we increase the price, then revenue starts to go down. So all we have to do is set the absolute value of the price elasticity of demand equal to 1 and solve for P. Now we'll answer this question. So the price elasticity of demand for our example is negative 800 times P over Q. We're setting it equal to 1, solving for P. But this equation right here has two variables, two unknowns, right? If you have one equation, if you have two unknowns, you have to have at least two equations. So we can make it to where we only have one unknown though, right? We can rewrite Q as a function of P. We know that Q is 10,000 minus 800P. Now we can solve the equation for P. So this is a multiplication symbol. The absolute value of negative 800P is just positive 800P over 10,000 minus 800P equals 1. So we have 800P equals 10,000 minus 800P. And then I'm just doing algebra here. Add 800P to both sides. 1600P equals 10,000. So P equals 10,000 over 1600, or $6.25, I believe, per unit. So if we're at any price below 6.25 and we increase the price, as long as we don't increase it above 6.25, then revenue is going to go up. But at any price higher than 6.25 or above 6.25, if we increase the price, where revenue is going to go down. So that answers the question there. Question 3. How can profit be increasing in the range 6.25 to 8.75? Despite the fact that revenue is falling? Well, the answer is pretty obvious. First, let's go to the picture. So we found this 6.25 number, right? That's somewhere like right here, which puts us down here somewhere on the profit curve. It doesn't matter where it puts us, but at that price, any price increase above that price leads to revenue going down. But it turns out that between the prices 6.25 and 8.75, profit is continuing to go up, despite the fact that revenue is going down. How can that happen? That's the question. Well, the answer is right here. This particular case. As price goes up between 6.25 and 8.75, revenue's falling, we know that, but profit's going up. Why? Because the variable expenses are falling faster than profit. So that's the answer. Once we go past 8.75, profit starts to go down. Why? Because the variable expenses are falling slower than revenue. Right? Between 6.25 and 8.75, revenue falls, but profit goes up because variable expenses fall faster than revenue. But after 8.75, revenue is still falling, but the variable expenses are falling slower than revenue, and that's why profit starts to go down. And then the final question, is the maximum profit the company can earn. And this is an easy one. This is just asking for this right here. At 8.75, what's the profit they could earn? Well, you just put 8.75 into the profit equation, right? Profit's a function of price. Negative 800 p squared plus 14,000 times p minus 60,000. And if we're trying to figure out the maximum profit, put in the profit maximizing price into the profit equation, right? So put in, well, I'll just say, maybe I'll just do it like this, p max squared plus 14,000 times p max minus 60,000 equals 8.75 squared here plus 14,000 times, and I'm writing very fast now, so my handwriting is really messy, but I think you know what's going on here. And if you solve this equation, you're going to get $1,250, I believe. Check to make sure that's right. But I'm going to label that here on the graph. So that's the highest profit they can earn. They can't earn higher than $1,250. If they try to charge a price higher than 8.75, profit will be lower than $1,250. If they try to charge a price lower than 8.75, profit will be lower than $1,250. If they charge 8.75, profit will be $1,250. And I think that's it for this video. There's one other thing I want to mention. Notice in this analysis, this pricing, in this particular pricing model, the price the company chooses doesn't depend on, to maximize profit, the price they choose to maximize profit, it doesn't depend on the fixed expenses. Those don't enter into the equation, right? If you recall the formula P max from the lecture notes, the price that maximizes profit is not, there's no F in the equation. Fixed expenses is right here. There's no F, right? Just A, B, V, 2, and B. You see A plus BV over 2B. So P max is independent of F. They're fixed, right? In this type of analysis, we're only looking at those things that vary. Those are the only things that could affect pricing. Those things that are fixed don't affect pricing. This concludes the video on pricing.